So, hello, you probably remember me from yesterday. I'm not going to use this. So, my name is Enrique, and I work in Conf. Those are two very important things I forgot to mention yesterday. So, second chances. So, I'm going to talk about Luas performance in general. And before I start, I want to give a shout out to Dash, who is a very great colleague of mine, who will take you out of your zone of comfort, and is also a very convincing person who can make you do things like do 2 talks when you want to do 1 talk. So he's also helped out organizing this workshop, so I want to and also, if anything goes wrong in this talk, it's his fault. Okay. So now let's begin. I'm going to make a quick intro about what I'm going to talk about, which is basically things that you can do on the Lua lamp and also on the C lamp in order to measure performance in Lua. And then at the end, I have some common pitfalls, and that serves as a kind of conclusion of the talk. So, intro is going to be very short. Lua has this binary nature in which you can attack problems from 2 sides or 2 lamps. One of them is C. This is how I always picture C in my mind because this is where I learned C, Turbo C++ from many years ago. And basically you can do a lot of powerful stuff on the C lamp, but they are usually not very portable, which is one of the strengths Lua has. On the other hand, you have the Lua lamp. Yeah, my graphic skills are not great. I don't have much back, so that's all you get. But the Lua lamp, you have the opposite. You don't have as many power as you have in C, but if you keep things Lua based, you can move the code around and do these tests in other platforms, pretty much everywhere where Lua is supported. So we are going to start with what you can do with Lua. So Lua lamp. Basically, your main tool is going to be os.clock, which has some quirks. For example, in Linux, it gives you CPU time, and in Windows, it gives you clock time. The difference between both is that clock time means that if your processor switches context and starts doing something else, and it gets back, that time is going to be included. On Linux, if it happens, you will not get that extra time doing an extra task that you were into. So there is already one quirk that you have to take into account. In addition to that, the units used are different or can be different depending on the platform. Linux and Windows is microseconds. Others can be microseconds or seconds or nothing, because sometimes OS is not available. I'm thinking, for example, embedded systems which don't even have an operating system. In that case, what you can do, for example, if you can use one pin to send a signal out there to some place where there is a block that you can activate and deactivate, and yes, still you're going to have an extra time sending that signal out. But if you repeat your test enough times to even out there, it's going to be fine. So, if you want to know more about OS clock, there is actually a very good resource here on the Lua users wiki, which you are probably familiar with already. And how do you use it with Lua code? Usually you use something obvious like this. You start at the beginning, you take the value of the clock, which is a number. You repeat the code that you want to test a certain amount of times, and then you get another lecture of a clock, and the difference is how much time did it take to run. Easy stuff. it can get a bit confusing when you want to take into account the garbage collector. Because, okay, if I'm testing this code 10 times and in one of them the garbage collector runs, my results are going to be weird. So one might think about running the garbage collector before the code, but obviously this is wrong, because if you do this, you are actually testing the garbage collector on each iteration. Basically, anything that you put between start and finish is going to be included on the results, and you don't want this. You might try to do something like this, where you move the start and the finish inside the loop, and then you collect your garbage just before. But this is also wrong in a more subtle way. The problem is the following. This line here. And why is that? It's because when you start measuring, you can think about the time starting here, right after the call to OS clock. Then your code gets run, and then this code also gets run, and it's also included in the test. Before, since start and finish were out of the loop, again, the extra cost of one function call was not significant. But here it's repeated on every iteration, so it actually adds up. So my intention here is showing that these apparently simple things are actually tricky, or can be tricky. So yeah, don't do this, because you are going to get, if you unroll the loop, it's going to look like this, basically. Now, one thing that you can do is actually stopping the garbage collector. That would look like this. Stop it at the beginning, get your start, do the iterations, finish, and then this part is optional. In this case, it doesn't make much sense, but if you're doing more stuff later on, you might want to reactivate the garbage collector. This also has problems. First of all, I think tests should mimic your production environment as much as possible. And if in your production system you are not deactivating garbage collection, you shouldn't do it in your tests either. The main reason is that you cannot solve your problems with garbage electrically, like here, all the time. You cannot be as happy as this couple here because of this. Regressions due to this memory trash. What this means is, if you have a way of doing stuff A, which is not very fast, but it doesn't generate a lot of tables or functions, so it doesn't manipulate memory a lot. And then you have another version of that algorithm, which is faster, but generates lots of garbage. And it means that the garbage collector is going to be run a lot of times. This second one can actually be slower than the first one on the long run when it's repeated many times. And that test that we saw before is not going to match that. It's going to tell you that the second one is faster. And that's basically the opposite of what it's supposed to do. So if you want to take into account, if you are not going to deactivate the garbage collection, you should probably do all the stuff. What I would suggest is concentrating on this line here. Basically, we have not treated or spoken about N quite a lot, so let's speak about it for a little while. One option that Hisham actually mentioned to me the other day was, making a formal study of your algorithm and coming out with a statistically significant number for that N. That takes a lot of effort, and actually, in reality, most people don't do that. So they do this. They wing it, okay? We wing it. And I would like to talk a little bit about how to wing it here. So this number is one of those things that you can never get too much of. If you do too much performance testing, usually not going to be bad. On the other hand, you can do too little. So what I would suggest is starting with a number that you know is going to be too big for your needs. And I usually don't like to think about it in terms of a number of iterations. I prefer a number of seconds that you want to have it running. For example, depending on the problem, it can be 1 hour or 1 day. So you start with something that you know it's going to be too much. And then gradually with time, you start reducing. So you start with 1 day, you keep working, maybe for 1 week, and then, hey, let's try with half a day. And if the numbers keep going the same way for 1 week, then you can say, okay, let's try with 5 hours, and so on, until you get to a point where, yeah, this is too long to feel. We have to keep the previous one. And then you have to wing it, and you don't have to do statistics or anything. It's this is, I think, it might sound a bit unscientific, and it is, but at the same time, I think it's better than what a lot of people do, which is just coming up with 10,000 iterations. It's a middle ground solution. And that's basically what you can do with Lua, pure Lua, in a Lua land. It gives you a number, maybe 2 numbers if you're measuring also memory consumption. That's all you get. And it's fine if you absolutely need to be portable. If you go to the CLAN and have more tools, you also lose that portability. And if you go that way, you can actually do, instead of measuring, you can do profiling, which is interesting. Profiling depends on what the operative system gives you. You cannot do it only with Lua. And this man here is one of the people that are, bleeding edge on that field. His name is Brendan Gregg, and he invented a tool I'm going to describe a little bit here, but not in depth. Because there is a talk from Egyptian from last year where he goes into the bare metal. So if you haven't watched it, it's a very good talk to basically learn about profiling. I'm going to just mention it quite quickly. So the operative system has to give you a way to make profiling. And I should have defined it a bit more. Basically, you want a report of where your program spends time doing stuff. That's the basic. Maybe we could call it resources instead of time, but you need help from the operating system to do that. Here are some of the tools you can use for that. And the problem is that all these tools generate, well, they look like this. This is pseudocode, even if it looks like Lua. You start the profiler, you do your execution, and then the profiler ends and it takes a dump, basically. And the dump looks like this. It's very, well, you don't see it very well on this projector, but these are actually very small characters. And this is a small sample. This is another one. I don't know if you can see the dots here, but they are like super small on my screen because it's a retina display, I can see them. But yeah, this is actually a lot of very tiny dots, each one representing 1 character, and this is like, I don't know how many lines, but it's basically impossible for a human to make sense of this without the help of a machine or an algorithm of any kind. So Brendan came out with flame graphs. This is basically the same that you saw before in a human-friendly way. And it's actually interactive. The thing is that for some reason you cannot make interactions on the browser as it is right now, so I have to open the image on a new tab and maybe get out of full screen. Yeah. Now, this is an SVG file, and you can actually click on it. For example, let me click on this function here, and it expands and shows you the detail. It basically represents how much time has been employed on, or has the CPU been on every function. And of course it's nested. The colors on this particular graph mean nothing. They are only a visual aid. These can help you find where your program is halting or is taking too much time. It's not the only kind of graph that is available. Here is another one. I'm not going to zoom on this one, but you can zoom and interact with all of these graphics. Yes. So this one is not about speed. This one is about memory. There are several ways you can graph stuff to know how your program is employing memory. One of them is simply mapping all the codes to alloc and free. This one is a bit different because operative systems have this concept of virtual memory and then real memory. And sometimes when you liberate memory, it takes a while before it's actually free. This is the kind of graphic that can show you that. In the words of Brendan, these can clarify things or not. That's what he said, and I have to tell him he is the expert here. But I think they are quite cool. Again, the colors don't mean anything, but he likes to give a shade of green or blue to the memory ones and more reds and yellows for the CPU ones. This is another one, another kind, which is the opposite of the CPU flame graph. In this case, what we are mapping is the time where our CPUs are halted. They are probably waiting for I/O, and this can help detect those bottlenecks where processors are basically doing nothing. This is never a good sign. And again, the colors mean nothing, but they are usually dark blue on the website. This one is different because the colors actually mean something. You can think about this as a difference flame graph. You take two of them, and then the colors will indicate whether one function has increased its time in red or decreased it in yellow. Blue. So yeah, this is the only one where colors actually play a role, and it's nice. That's how it is at the moment. This is the most you can get. What I would like to have, if I could dream the perfect ideal testing environment, would look a bit more like this. This is your typical Grafana, or there are many tools that you can use for these kind of graphics, where you take a lot of data and you present them for the human to consume. So what I'm thinking is, this one would show a big number, the time it took for the program to run, and then you could click on one of them, maybe see the flame graph on the other hand, and click on two sides and see the comparison, maybe filter and see just the evolution of some functions, stuff like that. This doesn't exist. This is a dream that I have. Maybe we will build it to come. I don't know. I also want to mention that in OpenResty, which is what we use in COM, they have several tools available already. We have been using them, not extensively yet, but we have been using them to generate some flame graphs of our happy paths and comparing the results so we can get regressions, at least on the most basic code path. So we had something, and we plan to improve on that front, but it's still not done. And finally, I want to talk about the common pitfalls. Since I was short on time, it's going to be only one pitfall. This one is the one I would that I think is going to be useful for the guys who are already familiar with performance and really knew all the stuff I talked about. So I want talk a little bit about love. You probably know it already. This is what introduced me to Lua. It's a game engine, and it's very simple and very friendly. And it has farming, where lots of people can be coming, like I did one day. So you get lots of newcomers, because video games are attractive, and students get excited about them. So they enter the forum and they start asking questions, as they should. So you get the how do I require a file from another file question. And then you get the second question, which is how do I make it fast? It's like, immediately, this is a search for performance. It's like many pages, you can search for fast in the forums and you get the same question again and again and again. My favorite is probably this one, but we'll make it a bit bigger. It talks about some unrelated stuff, and the last phrase is, am I doing this right? But would that be bad for my performance? And then he says, also, is there any trick that you could tell me to make it better? I also like that he is very polite. He says, please at the end. And usually in love, everyone is polite. And that's weird for these times on the internet. So, it's cool. So, it's my favorite one. And this illustrates the problem. People want speed. They want performance. The problem is that usually they want to get to that speed also very fast. And they just put on the Flash costume and it doesn't work. So they get rest and drive. And it's also difficult to explain because performance is one of those fields that actually involve many different factors that take time to learn. You cannot do performance with tricks really fast. You actually have to maybe go to school and learn about code notation and mathematics and all that boring stuff that takes time and you cannot learn it one evening. So you, as an experienced developer who knows all this, are faced with this problem because there's lots of people asking this all the time. Every day, 10 new people get to the forums and ask questions about performance. How do you deal with that? Because you don't want to become this, you don't want to invest a lot of time on this. Copying and pasting the same question also doesn't work because it makes you look like read the fucking manual, you knew kind of guy, and you don't want to do that. You don't want to sound like this guy, and it's difficult. So what I have found is that before pointing people to that manual, you have to give them something so they can change their mindset a little bit. In the old days, Bible had this concept of parable. A parable is a short story that makes easy to put an idea on a, in this case, on a simple mind. In our case, it's on a busy mind that wants to get to the results too quickly. Modern day parables in computer science are car analogies. That's what we do here. And I came up with one that I found it helps move people, nudge people in the right direction. And it's the following. You have a nice car, you want to make it fast. You don't change the paint of the car to make it fast. You have to actually go inside and maybe change the engine or the wheels, not just the paint. But this is what you are trying to do when you ask, is removing this if here is faster than using a ternary operator in Lua? Okay, so I have found that this one helps, but some guys can come back, I'm one of those guys by the way, come back and say, hey, planes actually, in planes it actually makes a difference what kind of paint you use or stuff like that. For those guys, well, they are not really for a solution. They are not really looking for a solution yet. They just want to be entertained. So those guys have this second version which says, unless the car is made out of paint. And this gets their mind like busy and they don't bother you again. So and everyone is happy, it's win-win. once you have their mind in the right mindset, you can actually give them the tricks. Because Roberto already has written these Lua performance tips, which looks in their tricks, so they enjoy it. One comment I would say is that when you recommend this week, you should say that the first page is the most important one. Because, again, we live in a time of very short attention span. And when you get a new book, you usually don't read the introduction, the first page. And in this case, it's the one that gives the tools, like, don't do it yet, make measurements, don't do it willy-nilly, this kind of stuff. And new guys and girls tell them to skip that and go directly to the tricks, which are what you would expect, how to make looks faster and things like that. And basically that's how you deal with the most common pitfall in Lua performance measurements. That's all I have. Thank you. Again, I'm not a super expert on this, but if you have any questions or maybe you want to ask about how we do it in long, I can answer. If I don't know how well or bad we are on time, I think that was fast, pretty fast. If you don't have questions, I have one question.
I have one question.
Okay, sure.
Those flame graphs, are they C function calls or
Yes.
Lua function calls?
Not all of them. The memory one, sorry, to go back. Go back. It doesn't work. Okay. Yes. This one is C function calls.
Mm-hmm.
This one is not. This one is, well, at some point it is, because it's the operating system doing stuff, and that stuff is probably C. But it's not yours, it's the operating system C. So, yes and no.
And is there a way to get a flame graph like this that shows you the Lua functions? Instead of just saying, oh, it's spending some time inside the interpreter loop.
Yes, I'm again not an expert, but basically generating all these graphs involves manipulating, these logs that you can barely read. But it's basically a huge log that you probably want to filter, like you would do on a regular log on a server. You just use AW key or something else, AWK, or grep or whatever, and you get your results, and then you do the graphs. It's the reason why I think it's not super popular is actually because it's a bit clunky. You have to use this Perl file to make a first pass, and then you use this other Python file to filter stuff out a little more, and then you get the flame graph. The tooling is not quite user-friendly yet. And lots of people build their own tools, like Engine, which is not here today, has contributed to this. So yeah, definitely look at this one. Illuminate.
I just had a comment on that. So there isn't a solution I know of from Lua, at least not what I'm looking for, but there was a solution based on what's called dtrace. So dtrace is this tool developed, I think, back at Sun Microsystems a while back, and it's like one of the best performance analyst tools ever made. Yeah. So anyway, but it's all for native code. So the problem is, when you step through it with your Lua stuff, you basically see all the C and low-level APIs,
Yes.
and you can't distinct, and you see C, you'll see the Lua C part of it, not your Lua functions. And now the Ruby, either the Ruby or the Python or both communities wrote some extension to dtrace, so it solved basically that problem. So they can actually see their Python code and not the underlying virtual machine. And so that's exactly what I'd like to see for Lua, but as far as I know, nobody actually implemented that for Lua. It was something that I was hoping to do some years back, but we just never get resources to do it.
happen to work at a lot of traits actually. And yeah, like if someone that actually knows how the integrated skills work, we can definitely help on that figuring out how to getting the traits code working. And like because you need to basically traits code decode the run in kernel to figure out what's the actual frame looks like and what's the actual Lua function you're inside the encoder. And if someone is interested in like working on that, we can.
I have used something similar in the past, not for traits but for GDB. There is a GDB script around that can, given like a Lua state pointer, it decodes so that it traverses the Lua state and like can essentially read you back a native like Lua stack trace out of that. So you go trace it into.
Could you send that to us?
Yeah, it's been years, but yeah, I'll probably still have it somewhere around it. I didn't write it, but I found it on the internet and I've tweaked it to like run to the latest GDB version at the time. So I should have it somewhere. Yeah.
Okay. Cool. You guys can continue. No, really. As I said, sometimes you make presentations to show what you know or what you have done. In this case, that was not the case. I volunteered to do this just to learn, so I'm quite open to suggestions and to fixes. And if I said something wrong, it's Ash's fault. Sorry.
I made him do it.
Yes. And one thing that I would say is a very important question, not technical, but from management, which is when to start doing performance testing. That's a hard question to answer. People want to do it from day one because, again, fast, speed, dressing up like flash, it's cool. Other people don't do it at all, and then their clients start complaining about, hey, this is not going fast enough. So there must be a point between one and the other, which is ideal. I would think that when speed is starting impacting your business, like, okay, now we have 100 users in this, and it's generating money already, maybe we should stop looking at performance a little bit. And also, I think it's quite important to have an automated system, so you don't have to go through the clunky steps every time you want to make a test of performance, like we have to do right now in Com. I think one engineer, one evening to produce the flame graphs, and that doesn't scale. So we have to get better on that. And for that, we need better tooling, or at least better documentation, like having everything in one place. Like, yeah, there's this script and this other script for this other tool. And at the moment, that doesn't exist. So that's all I want to say. Any more questions?
And also like cross-platform too, because like as you see there, there's like a tab that doesn't work in. So also Mac, there's a deep trace, doesn't work in Linux.
Yeah. Yeah, but that's the problem with C-land. You are not portable.
I can comment.
Sure.
I think that you should not mix performance considerations with optimizations.
Okay.
When we program, we are always concerned with performance from day one, and we should be. I mean, there are several solutions we don't even think about them because they are so absurdly slow. But if you really weren't concerned about performance, you would say, oh, just whatever you. And from day one, we are concerned about performance. The difference is optimization. We are concerned about improving the performance more than what would be the obvious way of doing things, or the, I don't know, the easiest, even the easiest, not the best, but kind of obvious solutions. And obvious already implies some or several performance considerations.
I have several comments on that. First, obvious. it's a very relative term. What is obvious to you might not be
I
obvious
think
to me.
anyone that learned programming and started programming already know. I mean, there are some stuff that people just don't do, and
It's
or sometimes they do, but
this guy does.
I don't know what he's doing. No, I mean there are some stuff that is so absurdly slow that it's impractical from day one. That's just not you can okay, it works, it puts us 100 elements and it takes 5 minutes to run. So performance is always concerned.
It is, I mean,
If you implement something and it takes 5 minutes to show a game that takes 5 minutes per frame, you are not concerned about optimizing. It's not working.
Yeah.
That's what I mean. So with performance is always in order. The problem is, as you said, about optimization. It's okay, it works, but it works for 100, it works for 1,000, but it doesn't work for 1,000,000, or it doesn't work. So I think there is this
distinction.
yes, this distinction, because optimization, I think I wrote that you should not think about that. But performance we are always thinking about. Or we should, as I said, if you don't really think about performance, you end up with a game that is the frame rate is one frame for 5 seconds, and that's just plain wrong. It's not perfect. You don't think that as a performance problem. I mean, you think that it's completely broken. The program probably you couldn't even wait 5 seconds before it's not working.
When a website doesn't load in 5 seconds, you are
Yeah.
It's true. I would say that the way I approach performance when a program is a bit different, or maybe it's the same but said differently, which is that I like to make programs that I can change easily. So when I see a performance issue, I can modify them easily. So it's like the car analogy of again. I want to be able to change the engine and change the tires of the car quite quickly. So when optimizations get in the way of those changes, they might give me small benefits, but if they prevent me from making those big changes that actually improve performance quite a lot, for example, changing the algorithm that you use or sacrificing more memory in order to get more speed, that's where I really think, yeah, I'm not going to do this now. I actually almost never end up doing, real fine-tuning changes. Like, okay, here I need to make a numeric loop, otherwise it's too slow. I have never actually found that limit, because usually there are other stuff that I can do that makes bigger improvements somewhere else, because the code was easy to change. So at the end, for me, optimization is actually more related with resistance to change and you managing change in code. That's my idea, and I think it's similar. I still think about performance, but from the point of view of changing code.
It's simple.
Okay.
And I have another question.
Sure.
Can you explain the flame graphs?
Explain.
What does it mean?
Yes, yes.
Flame graph?
I'm going to explain the one I understand completely. Okay, because the others have holes that I don't understand completely.
Enrique, can you show it on a browser so you can zoom in?
Yes, yes, yes. I did that before, but maybe I did it too quick. Let me. Come on. Yes. Flame graph. Okay. This image is the same as this image, and this is an SVG file. It's an XML which modifies. Oh, I'm not sure I can do that. Let me try. Yes, yes. Okay, cool. Thanks. Yes. So at the bottom, you see all. It's called all. Maybe this one here. The function. That's all. That's everything that you did. basically, since the provider started until it ended.
I think this one's already zoomed in.
Yes.
Staff would already clicked on something. If you go like reset zoom.
Let me see.
Yeah.
It's still all at the bottom, I guess. Okay, so yeah, this shows MySQL doing stuff, and again, this shows MySQL doing stuff thousands of times. Then you get how much time in total was spent on each function. So if you go up, these are function calls. Okay? The colors mean nothing, and the order also means nothing. If you see one next to the other, like here, that doesn't mean that one happens after or before.
What means?
What means what?
What means anything?
Yes,
Order doesn't mean.
the width means time.
Okay.
In total. Okay, so the bigger the wider the line, the more time has been spent, the CPU has spent on this function. And then you can click and it expands basically.
Enrique, isn't the vertical, is that what you call the call stack or the
Yes.
change
Yes.
function?
Each vertical line is a call stack measurement.
No, sorry, you're trying to frame.
Yeah, that you measure from that big dump.
I didn't get the first part of your phrase for that.
If I remember correctly, that big dump, each measurement it's a snapshot of the call stack at that moment, right?
Yeah.
And then basically,
No, it isn't. It's similar to that.
same.
No. It's a good point. But if you have a branch inside a call stack, and half of the time you do one set of functions and the other one you have to do another, on this frame we are going to have both. You are going to have how much time was on each one, but you are not going to
He's talking about the original snapshots that you get in the dump.
Okay, yeah. This
Yeah,
This
so
one.
that, the big one.
it's actually, well, you cannot see anything here. It's similar to a tree. This one is similar to a tree when you use the command line tree on your folder, and it shows like it has lines graphically showing the call stacks, and then it has numbers saying 1 microsecond or 2 milliseconds or something.
Back to so the function is called by different functions.
Yes,
It will appear multiple
it should appear
times.
multiple times here.
So that you don't have a total for that function.
But all of these graph, but that's the thing. In order to generate this, you have actually manipulated that very big file the way you want it. This is one example of one of the kind of graphs you can make. You can probably manipulate the text in another way to generate one that doesn't take into account from where the function is called. The idea is usually finding the or the wider function calls and then optimizing those.
But not exactly, because it may not be right because exactly it's working necessarily directly.
Yes.
Yeah, but you're worried about. Yeah.
Yes.
Which is the operation, yeah, the overall operation.
What I want to stress here is that there are many kinds of graphs. I have shown 3, but they actually represent a whole class on their own. Like the memory ones, there are like 4 or 5 different ones that you can make. CPU one is the
I'm
same.
trying to understand why this is that why that this would be better than Chickoff listening.
I don't know that tool, so I cannot compare them. Sorry.
The prompt just says how the call each function was used without saying who called who.
Okay. Yeah, then you have the opposite problem. You want to know from where, like in some cases, you might have a function here, 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 and then a big call to that function here. This way you can know that that's where you want to optimize. So
For
it's
instance, looking at that graph, what would you worry about?
I'm I don't know my SQL. So
But you should, if you look at the graph, probably there is something visually.
yes, I would say that there are two main areas already, which is actually by the end you can use it. It's index and to select. It's kind of indicative of what it's doing. Here it's building some internal structure and then it's passing it probably here. So you can already see if that's one of my problems actually with flame graphs. I think they are most useful when you look at them from a time perspective. You were saying something?
Yeah, so flame graphs are useful because they represent a ratio as you go up and down the call stack. So as you find a particular frame that you might consider expensive, if you're designing your application or your algorithm in such a way that you know that that part of the stack is not supposed to be expensive, that's where flame graphs are useful. So if you see something is taking up 30% of your time, where it's supposed to be something that was optimized away or should be JITted but isn't, that's where these graphs can become useful, is now you can pinpoint and profile in your application, this is supposed to be taking up a lot less time than it is. Or alternatively, if you see something that's taking up 80% of your time that you know is expensive and there's nothing you can do, this lets you pick at the remaining 20% of functions that are at that same level in the call stack that you can continue to optimize there. So it's not necessarily this part of the call stack took X amount of time, it's this part of the call stack took a ratio of our overall execution time, and based on the architecture of the application, I can know whether or not that's good or bad. The other thing that you do is as you make changes within your application and generate multiple flame graphs, as that ratio changes, if you make a single change and part of your stack goes from 30% execution time to 45% execution time, if that was a desired change, great. If that was an undesired or unexpected change, now you know that you made a change somewhere in the stack that you weren't expecting. You need to understand why that change occurred. So it gives you visualization in your call stack, but what you do with that depends on the nature of your profiling and depends on your application.
As often happens with computers, everything depends on something. Yeah, in order to come, I think what is missing here is really a way to compare time series. Here, you can compare two with this. That's actually it doesn't show very well, but there are more blues and reds here on the screen. But yeah, the time component is missing on this tool. But the idea is comparing as you do changes to the code. Also, one advantage that this has of the tool that you mentioned is that this comes with heuristic, so we can use it quite easily.
But my point is that usually you use graphs when the visual image gives you some clues by the image itself. That you don't need to read the tables to see, oh, this is that function. The labels are just extra information. But the visual format of the graph should call attention to problem. Otherwise, they are not. I mentioned they are better than tables, or just the information. So that's when all the reasons before thinking for them are not visual. No, they have this information. Okay, but the tables don't have this information for me. But if I have to read the name of the functions to know what the graph means, to know where to look at in the graph, then I prefer a table that is easier to read. Graphs are good exactly because this is the, for instance, a pie graph, you see this is it. So I don't know what it is, but this is where I have to look. And here it's kind of all depends that it's big, but it should be big, and that is small, it should be also I have to really understand.
Maybe it's a matter of
the image itself is not as I asked that. Show an image, so where should I look at that image?
Yeah. Maybe it's a matter of getting used to the tool. Like the first time you start driving a car, it takes a while, and this is a tool that requires getting used to.
I think one of the reasons that this is popular also is because they're dealing with like stacks of different third-party components. So it's not about like understanding your code as much as understanding an entire application that's composed of many like your parts and third-party parts and how they interact with each other and how they affect each other. So,
Right.
Yeah. We can continue later if you want. you very much.